The industrial systems of the early 19th century were built according to standardized measurements, interchangeable components, and coordinated supply chains that connected distant manufacturers across continents. By 1820, factories in Manchester could order precision parts from Birmingham workshops without sending blueprints. American rail companies used identical gauge specifications across state lines before any federal authority mandated it. Canal locks in New York operated on the same dimensional logic as those being constructed simultaneously in the English Midlands. The official explanation is straightforward. Trade networks published technical manuals and professional societies disseminated best practices rapidly during the Industrial Revolution. But the Erie Canal was designed between 1817 and 1825 by engineers with no formal training in canal construction. The United States had no established engineering schools. The chief engineer, Benjamin Wright, was a surveyor. His team built 363 miles of functional waterway with 83 locks, all dimensionally consistent, all compatible with boat designs that hadn't yet been standardized. They specified masonry tolerances, gradient calculations, and load-bearing capacities that matched European practice. But the manuals explaining those practices weren't widely available in rural New York. The construction didn't slow down while they figured it out. It proceeded as though the knowledge was already in place. This is an investigative documentary. We're not presenting conclusions. We're examining observable patterns in historical infrastructure that feel internally inconsistent. All interpretations remain open. The goal is examination, not persuasion. The same year the Erie Canal broke ground, Britain began constructing the Caledonian Canal through the Scottish Highlands. Different continent, different government, different workforce. Yet both projects used nearly identical lock chamber dimensions, approximately 40 feet wide, 165 feet long. Both calculated water flow rates using similar hydraulic formulas. Both addressed frost heave and masonry using comparable foundation techniques. No international engineering conference had occurred. No governing body had issued these standards. The consistency exists in the infrastructure itself. Between 1815 and 1835, dozens of canal systems were built across the northeastern United States and industrializing Britain. They shared load calculations, drainage engineering, and even aesthetic choices in stonework. Observers at the time noted this uniformity, but typically attributed it to modern practice. A phrase that assumes consensus without explaining how that consensus formed so quickly after the Napoleonic Wars disrupted European communication for over a decade. The timeline compounds the friction. In 1816, massive crop failures struck the northern hemisphere, the year without a summer, caused by the eruption of Mount Tambora. Famine followed. Governments were destabilized. Migration patterns shifted. Yet within 18 months, coordinated infrastructure projects began on both sides of the Atlantic, all operating from what appears to be a shared technical foundation. The knowledge didn't develop gradually. It appeared in application. Railway construction demonstrates the same pattern with even greater precision. The Stockton and Darlington Railway opened in 1825. The Baltimore and Ohio Railroad began construction in 1828. By 1835, both systems, and dozens of others across 2 continents, had converged on a standard track gauge of approximately 4 feet 5 inches. This wasn't legislated. It wasn't the result of a single inventor's patent spreading through licensing. It emerged as a de facto standard before the institutions that typically enforce standards had been created. The uniformity extends beyond dimensions. Early railways used similar signaling logic, comparable safety protocols, and consistent approaches to gradient management and curve radius. These weren't simple choices. They required calculating load stress, understanding momentum physics, and predicting long-term material fatigue. The engineers building these systems were working from principles that don't appear in the written record as uncertainties. They appear as assumptions, as if the trial and error phase had already occurred. Warehousing systems in port cities present the same friction. Between 1820 and 1840, London, Liverpool, Boston, New York, and Philadelphia all constructed multi-story brick warehouses with load-bearing designs calibrated for specific weight distributions. The buildings assumed standard barrel sizes, standard crate dimensions, and standard shipping weights, but those standards hadn't yet been formalized by trade organizations. The architecture predicted the standardization. Textile mills in New England were built between 1810 and 1830 with water-powered mechanical systems nearly identical to those in Lancashire, power transmission shafts, belt drive configurations, and loom spacing that matched British factories despite no American workforce having trained in those facilities. The machinery wasn't imported whole. It was reproduced locally with dimensional accuracy by craftsmen who had never seen the originals. The transfer of knowledge happened, but the mechanism of that transfer remains unclear in the historical record. Gas lighting infrastructure rolled out across major cities in the 1820s and 1830s with pipework that used compatible threading, pressure ratings, and valve standards across national borders. Water systems followed the same pattern: pipe diameters, joint fittings, and pressure management strategies that appear uniform before regulatory agencies existed to enforce that uniformity. These weren't accidents. They were coordinated material choices that required shared technical assumptions about flow dynamics, material stress, and long-term infrastructure maintenance. The systems assumed continuity. They were built as though they would need to integrate with future systems that hadn't been designed yet, and somehow they did. The urban gas networks of the 1820s were expandable in ways that only make sense if the builders anticipated decades of growth according to principles that wouldn't be formally documented until much later. The infrastructure feels like it was designed with future compatibility in mind. But compatibility with what? With systems that didn't exist yet. Systems that would be built using the same unspoken standards. And those standards, those hydraulic formulas, material specifications, load calculations, they don't appear in the record as discoveries. They appear already in use, already trusted, already applied at scale across regions with limited communication infrastructure and no central authority coordinating their technical education. The pattern isn't hidden, it's structural, and it continues into unexpected domains. Administrative systems mirror the same pattern. By 1830, census methodologies in the United States, Britain, and parts of Western Europe had converged on similar categorization systems: household size, occupation classifications, age brackets, without a coordinating international body. The forms looked different, the languages varied, but the underlying logic of how populations were measured and sorted followed comparable structures. This wasn't imposed from above. It emerged in practice simultaneously across governments with different political systems and bureaucratic traditions. The U.S. Census of 1830 used occupational categories that closely matched those being developed in Britain's industrial surveys, despite no formal exchange of methodology between the two governments. Both systems distinguished between manufacturers, commerce, and agriculture, using similar definitional boundaries. Both tracked urban density in ways that anticipated infrastructure needs that hadn't yet been articulated as policy goals. The data collection assumed future use cases. Prison systems show the same administrative synchronization. Between 1820 and 1840, penitentiary models in Pennsylvania, New York, and England adopted similar cell dimensions, surveillance architectures, and record-keeping systems. These weren't just philosophical alignments about criminal reform. They were material choices, door widths, corridor lengths, sightline calculations, that required shared assumptions about human movement, security protocols, and long-term facility management. Auburn Prison in New York opened in 1816. Millbank Prison in London opened in 1821. Both used radial designs. Both implemented silent systems. Both maintained prisoner logs with nearly identical data fields: name, age, crime, sentence length, behavior notes, health status. No international prison standards existed. Yet the systems operated as though they did. Public school buildings constructed in the 1820s and 1830s across New England and the British Midlands used similar classroom dimensions, roughly 25 by 30 feet, with ceiling heights between 10 and 12 feet. These proportions weren't arbitrary. They reflected acoustic calculations, lighting optimization from large windows, and assumptions about classroom size, typically 30 to 40 students, that wouldn't be formalized in educational policy for another generation. The architecture predicted the pedagogy. Hospitals present an even sharper version of this pattern. Pavilion-style hospital designs emerged nearly simultaneously in the 1820s in London, Paris, and Philadelphia. Long, narrow wards, high ceilings, large windows on both sides for cross-ventilation. The layouts assumed germ theory principles, isolation, air circulation, sanitation, that wouldn't be medically accepted until the 1860s. The buildings were designed for a medical understanding that didn't yet exist. Or they were designed according to principles that existed in practice but not in published theory. Urban planning in rapidly growing American cities between 1820 and 1850 followed grid systems with block dimensions that facilitated future infrastructure installation. Sewers, gas lines, water mains, before those systems had been designed. The streets were wide enough for equipment that hadn't been invented yet. The lot sizes accommodated building footprints that wouldn't become standard until decades later. Philadelphia's grid, established in 1682, was an outlier. But the grids laid out in the 1820s and 1830s, Chicago, Detroit, Indianapolis, assumed densities and utilities that didn't match their contemporary populations. They were built for cities that didn't exist yet. And those cities grew into the infrastructure as though following a template. The Erie Canal's economic impact was predicted with surprising accuracy before construction began. Projections from 1817 estimated trade volumes, toll revenues, and regional population growth that would result from the canal's completion. Those estimates, made by legislators and surveyors with no prior experience in canal economics, proved remarkably close to actual outcomes measured in 1835. How did they calculate future demand so precisely? Railway companies in the 1830s issued bond offerings based on revenue projections that required assumptions about freight tonnage, passenger volume, and regional economic integration that hadn't yet occurred. Investors trusted these numbers. The bonds sold. And the railways, once built, generated revenues that matched the early projections with unsettling consistency. The financial models assumed a coordinated economic system. But that system was still forming. Grain elevators in Buffalo and Chicago, constructed in the 1840s, were designed with storage capacities and loading mechanisms that anticipated standardized rail car dimensions and shipping container volumes that wouldn't be formalized until the 1850s and 1860s. The buildings were over-engineered for their immediate context. They made sense only as part of a larger system that didn't fully exist yet. Telegraph networks, rolled out rapidly in the 1840s, used pole spacing, wire gauges, and relay station distances that were consistent across different companies and regions before any regulatory framework existed. The infrastructure was compatible by design, as though built according to a shared specification document that no one can locate in the historical record. Street lighting systems expanded through cities using lamp post spacing and illumination coverage patterns that matched across municipalities with no central planning authority. The consistency suggests either widespread copying, but from what original? Or adherence to standards that were understood but not codified. Fire hydrant placement in growing cities followed similar logic. Hydrants appeared at intervals that optimized hose reach and water pressure distribution, based on calculations that required understanding urban fire spread patterns and hydraulic engineering. These weren't guesses. They were applications of existing knowledge. But the manuals explaining that knowledge are sparse or absent from the archives. Bridge construction during this period shows the same technical synchronization. Suspension bridges built in the 1820s and 1830s, in Britain, France, and the United States, used comparable cable calculations, tower foundations, and load distribution strategies. The Menai Suspension Bridge in Wales, completed in 1826, and various American suspension bridges built in the 1830s operated on similar engineering principles despite limited direct communication between their designers. The knowledge transferred somehow. Through correspondence, through published drawings, through traveling engineers, but the speed of that transfer and the precision with which it was applied in diverse contexts creates timeline compression that feels inconsistent with the communication infrastructure of the period. Postal systems expanded in the 1820s and 1830s with sorting facilities, route optimization, and delivery schedules that assumed literacy rates and mail volumes that matched actual growth with minimal adjustment. The systems were sized correctly from the beginning. No trial period. No gradual scaling. The infrastructure appeared at the scale it needed to be. Banking architecture from this era, vaults, teller configurations, security systems, shows cross-regional consistency that suggests shared assumptions about transaction volumes, currency standardization, and fraud prevention that were being formalized in practice faster than in regulation. The buildings knew what banking would become. Custom houses at major ports used nearly identical inspection procedures, tariff calculation methods, and cargo documentation systems despite operating under different national governments with different trade policies. The administrative apparatus was structurally similar even when the laws being enforced were different. The systems assumed interoperability. Courthouses built in the 1830s across the American Midwest and British provincial towns used similar floor plans. Courtroom dimensions, judges' bench positioning, jury box layouts, public gallery arrangements. These weren't symbolic choices. They were functional designs based on assumptions about legal procedure, crowd management, and acoustic requirements that don't appear in written guidelines from the period. The architecture encoded procedural knowledge. And that knowledge was consistent across jurisdictions with different legal traditions. Whether this reflects inherited organizational logic from earlier systems, convergent problem-solving under similar constraints, or transmission of technical knowledge through networks that aren't well documented in traditional archives, these remain open interpretive questions. But the pattern is observable. Systems built between 1815 and 1840 operate as though designed by people who already knew what worked, even when those people had no documented prior experience. The infrastructure assumes expertise, and the scale of that assumption, replicated across continents, creates friction with the narrative of gradual industrial learning. The term Tartaria appears on European maps from the 16th through 19th centuries as a geographic label for the vast interior regions of Asia, areas that were poorly understood by Western cartographers and often conflated multiple distinct cultures and political entities under a single name. It wasn't a unified empire. It was a convenience term for unmapped territory. In recent years, the word has been reinterpreted as a framework for questioning the continuity of industrial-era infrastructure. Not as a literal civilization, but as a label for the possibility that early 19th century systems inherited more than they invented. Three interpretive models exist. The first, rapid knowledge transfer through informal networks. Traveling craftsmen shared technical drawings, correspondence between engineers, moved faster and more effectively than formal institutions, creating apparent simultaneity that was actually coordinated dissemination. The second, convergent problem-solving under similar constraints produced similar solutions independently. Cities facing comparable challenges, sanitation, transportation, communication, developed comparable infrastructures not because they shared knowledge, but because they faced identical pressures. The third, some organizational and technical knowledge from earlier periods persisted through the disruptions of the late 18th and early 19th centuries in ways that aren't well represented in surviving institutional records, creating the appearance of sudden emergence when the knowledge was actually continuous but informally transmitted. None of these interpretations are conclusive. All are consistent with observable patterns. The year without a summer in 1816 marked a turning point. Crop failures, economic destabilization, mass migration, and then, within a few years, coordinated infrastructure development on a scale that suggests either remarkable recovery or continuation of capacities that survived the disruption. The Tartaria framework, in its modern usage, isn't a claim about a specific lost empire. It's a metaphor for the gaps in the record, the moments where infrastructure appears more coordinated, more sophisticated, more forward-thinking than the documented institutions of the period seem capable of producing within the available timeframes. It's a question about inheritance versus innovation. The evidence doesn't resolve that question. It keeps it open. Census records, canal dimensions, railway gauges, warehouse designs, administrative forms, prison architectures, hospital layouts, street grids, banking procedures. all of them appearing with structural consistency across regions during a period of rapid change and limited formal coordination. The systems worked, they integrated, they scaled, and they did so as though following principles that were already established, already trusted, already applied at a level of sophistication that feels compressed in time. Whether those principles were transmitted through networks we don't fully see in the archives, whether they emerged independently through parallel development, or whether they represent continuity with earlier organizational systems that left less documentation than the physical infrastructure itself, these possibilities remain equally available for examination. The infrastructure is still here. The canals, the railways, the buildings, the administrative structures. They can be measured, compared, analyzed, and the patterns they reveal continue to invite investigation, not as mysteries to be solved with a single explanation, but as evidence of historical complexity that resists simple narratives about how knowledge moved, how systems formed, and how quickly coordination could occur in an era we typically understand as fragmented and slow. The question isn't whether Tartaria existed as a civilization. The question is what we call the patterns when infrastructure behaves as though it remembers something we don't have records of. The documentary ends here. Not with answers. With the persistence of the question itself.